L'Hopital rule, I just screamed into microphone, poor people. L'Hopital rule, I did not know it has the silent S over here. So this S is not pronounced. And I also did not know it has H. So in Russian, we say L'Hopital with no H, no S, and nobody cares, to be honest. In my language, there is a nice notation, it's not international notation, to put it in the circle L. But because it has L and H in English, many people put it in the circle when they perform it. Because L'Hopital's rule and L'Hopital's technique is so unusual that if you don't put the notation, later you might forget what the heck did you do. Why the derivative suddenly showed up in the limit. But it's very pleasant technique. So there's lots of jokes about hospital and limit is taken to the hospital and L'Hopital rule solves the limit. Okay, there's lots of fun stuff about that. So we're gonna work on 3 cases and then we're gonna add more, actually not 3, 2 cases and we're gonna add more later. Bless you. Okay, case number 1, oh wow, that's very fat. When you have a limit of 0 over 0. So a function divided by a function, and for some reason it becomes 0 over 0. And the other one will be infinity over infinity, and sign doesn't matter. So it only works for these 2 cases. You will like L'Hopital rule so much, you will start applying it everywhere. So we're going to be reminding you cannot do that. It's just really pleasant rule. But you can only do it 0 over 0, infinity over infinity. So just a second. The whole point of the rule is this amazing formula. Instead of working, so I put LH in the circle. You don't have to do that. That's just a notation. And actually, I don't see this notation in America, so no need to do it. But I do it in my notes, and I like it. Like I mentioned, it tells you what the heck did I do. I forget all the time. I'm pretty sure you too. When you have f divided by g, and you don't like those functions, for example, they're hard or so on, why? You can actually take derivative of f separately. Take derivative of g separately, not quotient rule. And instead, work with quotient, with those derivatives. That's awesome, because derivative of x squared is 2x, much easier. Derivative of 2x is 2, even better. Derivative of 2 is 0. So if you can work with derivatives and it's legal, why not to do that? And we're going to be doing that all the time, and you will love it. Yes?
If lim x approaching a f of x over g of x is equal to 0 to 0, and lim x approaching a f of x over g of x equals lim x approaching a f of x g of derivative of f of x derivative of g of x, then doesn't that mean derivative of f of x over derivative of g of x equals 0 over 0?
Yeah, it does. It does. Very clever question. Isn't then this the same thing? So that means this will be 0 over 0. The answer is yes. So the technique will help us to find limits easier. And sometimes you can do it second time until it's not 0, 0 anymore. But the whole point you will see in a second, it makes your job easier by taking derivatives. And that's why you struggling to take derivatives, say chain rule was complicated, but you will see already after starting this chapter, derivatives is a tool. It's everywhere. Right now we're using it to solve limits. We'll be doing approximations and everything, integration also. You must know derivatives like alphabet of a language. Mathematical language consists of derivatives. So that's it's not even an achievement yet to know derivatives. Like it have to be engraved into your memory and your hand so you can do it fast. That's how good you will be good at that. And don't be scared, you will be. It's inevitable. I like this word, inevitable. So let's do this famous example, limit sine x over x. Limit sine x over x is so well known, I call it famous, but they told me you're not supposed to call equations famous. Apparently only people are famous, or historical events, right? That's what someone told me. So equations cannot be famous. I kind of very doubt about that. But this formula is so known and amazing that it has a name in my language. We call it a wonderful limit. It's actually called there's a Wikipedia page called Wonderful Limit, and this limit is there. So I learned it as a wonderful limit. In English, you guys kind of boring. You don't have any name for that.
Well, there's no rule in English against calling things that are not humans famous. So I think it's just a math.
No, someone told me though. Anyway, whatever. So do you know the answer for this limit?
1.
It's 1. Yay. We learned it before. I think I already mentioned it was wonderful limit. And finally, we can tell you how it was derived. There are many ways to do it. But let's see why. So sine x over x when x approaches 0. Let's check numerically. You can use any kind of tool, including calculator or not. What happens when we are close? Well, 0.5 is not very close. Close to 0 from the left and from the right. Then I will have sine of 0.05. That's why you don't like working with limits, but actually you can always check numerically if you're right or not. Sine of 0.05 over 0.05 is approximately, don't forget to convert to radians, 9 if needed, 792, 0.0499792 over 0.05, and then that's approximately 1. And then you can do something smaller like 0.03, and it's approximately 1. So numerically it works. How about algebraically or calculusly, using calculus? And then I will show you graphical. Actually, the second one should be graphically. Graphically, look at this beautiful picture. I draw two functions for you. Y equals sine, and in green one, y equals x. And we're looking at the ratio, but not everywhere. Not like, so the limit x approaches not 5. Okay, it's like not over here. I don't care about that. Not minus 15, not here. I don't care about that. I'm caring about 0. What is happening around 0? And I mentioned before, if you zoom in a lot, they're the same. Around 0, sine has slope, same slope as x. Y equals x, which is a line. That means over here on this interval, you can use a line instead of sine. That's called linear approximation. We did it before. We're going to do it again. That's a song. So compare that. Finally, 3. That was 1, 2, and let's do 3. We're going to use L'Hopital's rule. Limit sine x over x. X approaches 0 equals. You cannot use L'Hopital rule if it's not 0 over 0, infinity over infinity. So I have to check that. Sine at 0 is 0, x at 0 is 0. Yes, it is 0 over 0 case. You don't have to have this notation. I will never require that. But I will tell you, you will see this notation around the different books in Europe, in Asia, and in the United States. So 0 over 0. That permits me to use L'Hopital's rule, especially the circle. They don't do it here. I like it though. That means I will write down limit x approaches 0, and instead of working with original functions, I will take derivatives of them separately, not quotient rule. That's why it's so easy. Derivative of sine is cosine. Well, that did not make it easier. Cosine is not better than sine. But derivative of x, 1. Can you now solve this limit? Yes. You plug 0, cosine of 0 over 1. What is that? 1. Boom, in 5 seconds. 5 seconds. L'Hopital rule is amazing. So again, several things to remember. Must be 0 over 0. Take derivative, take derivative. And instead of working with original functions, we work with derivatives. Should I write it carefully more, or you got it? So there's some cool notation that, I guess, explanation or work. It was limit f of x over g of x as x approaches 0. And then we wrote down limit f prime over g prime. And that was cosine x over 1. Maybe like once to write down for you to have good notes. But in general, you take derivatives and you're happy. And that's why if you don't put a note to yourself, what did you do? It's kind of awkward. In the month you will look at this, why sine x over x became cosine over 1, especially if it's not that obvious. How did it happen? So that's why I like to put this notation, because that does not leave any questions. Oh, you did L'Hopital rule. So that's why. And your brain will recognize that. Let's practice more. Yes?
If they're the same, then what changed to make it not 0 over 0, or what new information is there that we can now find?
Oh, I see. Yeah, that's linear approximation. Good question. So basically your question is, how does it helpful or something?
Yeah.
Yeah.
I see that it's helpful, but I don't know why it would change anything.
Yeah, I will actually, in my plan, I will show you animation after this let's do more examples to have good practical solutions. But it's a good question. How do we want to use it? What's even the big deal here? Yeah, stay put just a second. Example number 2. So this example just had 3 different ways of solving it, but it was example number 1. So we did numerically, just plug some number close to 0. Graphically, we checked the ratio, and we found slopes of those ratios. But slopes are derivatives, so L'Hopital rule is the best one. Let's do more. Limit of. Now we can be working with lots of ratios. E to the x minus e to the minus x. 2 sine x. X goes to 0. X goes to 0. Yeah, that's like, what is that? How do you, remember we learned limits in August 16 and 18 and 19. The first step is do some algebra. What kind of algebra are you going to do here? Too annoying. And that's why so many students approached me and asked, can I use L'Hopital's rule? And I said, yes. See, since you know L'Hopital rule, you can use it. So now everyone know L'Hopital rule. So let's check first if I can use it, because don't use it when you cannot. E to the 0 is 1, not 0. E to the minus 0 is also 1, but 1 minus 1 is indeed 0. And then sine of 0 is 0. So I'm allowed to use L'Hopital's rule. Agree? Good. And now you can help me. E to the x prime gives me e to the x minus e to the minus x.
Minus e.
Minus e.
So it would be e raised to power x plus e raised to power x.
Okay, more answers. People at the back. Wait. Let's see. People at the back. Do you know? Minus or not minus? How many minuses do we have? 4, 7? Does anyone know? Let's do it slowly. Copy the function first. That's the whole idea with exponential functions. Times derivative of the function inside, since it's chain rule. And the function inside is minus x. Derivative of minus x is minus 1. So it's going to be e to the x plus e to the minus x. Derivative of sine is cosine. Doesn't really make it better, but it does, because cosine of 0 is not 0 anymore. So let's see what did we end up with. We have e to the x plus e to the minus x. Now it's not going to be 0 anymore. And cosine of 0 is also not 0. You can plug in your 0 and find the answer. The answer is going to be
2 by 2, 1.
Oh, you're fast. E to the 0 plus e to the 0 over 2 times 1. I'm plugging in x equals 0. That is 2 divided by 2, right? Which is 1. Put it in the box. Is this weird? What do you think? Is this weird? Is everything weird? Is life weird? That makes sense? So why did we do it? There was 0 over 0. You have to factor. Common denominator. We don't like that. Remember multiplying by conjugate? Screw all of that. Just take derivative of the top. Take derivative of the bottom. But only if you can. 0, 0, infinity, infinity. Then it fixes everything. And if not, you do it one more time. And sometimes one more time fixes everything. So that's my idea here. L'Hopital's rule. Not too bad. More examples, and then I will show you some cool idea and animations. Limit. So these kind of classical problems are going to the exam. X squared over e to the x. X goes to infinity. Again, you know, even with the previous example, you could actually check your answer. Plug the previous one. Plug something small, 0.001 in your calculator, and check what is happening with e to the 001 plus e to the 0, blah, 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 and over 2 cosine of 0. And it should be around 1. So that's how you can actually always check the answer. Not always, but you can try. With this one, it's infinity. Why not to plug million squared over e to the million? Which, and I told you, my way of seeing it is the competitions of 2 giants. 2 explosions. One explosion is at the top and another explosion is at the bottom. Which explosion is going to win? Explosion of the top wins, everything explodes to infinity. Explosion the bottom wins, everything shrinks to nothing, right? Which one wins?
The bottom one,
The bottom wins, so the answer is
0.
0. We know the answer, which is nice. Now let's check it using L'Hopital's rule. So that's how I explain to you. And then many professors, they require to use L'Hopital rule. They don't explain these ideas of competitions of speeds. I love this idea. So let's do L'Hopital rule. Let's check if I can. Infinity squared is infinity. E to the infinity is definitely infinity. That's for you to know. E to the minus infinity is not infinity. And e at x approaches to 0 is not infinity. So you make sure you know your exponential functions from the last quiz. Graphs, what happens when you flip it, and so on. And what if it's not e? What if it's 0.3 to the x? That's a completely different story now. So now you know. That's working with exponentials. Anyway, you should finish before me. Who can finish faster than me? L'Hopital rule. I will take derivative of x squared becomes 2x. And e to the x is e to the x. Did not really help. I still can compare though. 2x is definitely slower than e to the x. So we still know it's 0. But from L'Hopital's rule, it did not really make any difference. So I'm going to check it again. It's infinity over infinity again. And I can apply L'Hopital rule again until it's not infinity over infinity anymore. Or 0 over 0. So I'm going to differentiate it again. And because it's x squared, it makes sense. I will differentiate it twice to get rid of the x. Now it's very obvious. Denominator goes to infinity, numerator is a number. Number over infinity is 0. How do I know that? In many ways we covered in previous classes and the quiz. It's 2 e to the minus x, and we know e to the minus x shrinks to 0. Or it's dividing by infinity. Well, 2 divided by infinity. Any way you like it. Can we do one more L'Hopital rule to have like that 0? Because derivative of 2 is 0. Can we do that? No. Because it's not infinity over infinity anymore. Now it's 2 over infinity, so we cannot perform L'Hopital's rule. So don't do too much. The answer might not end up to be good. So that is the idea. And one more example. Put it in the box. Finally, example 4 is, that's classical, your favorite examples at infinity. X squared, well, actually it's not at infinity in this case. X squared minus 2x, x cubed plus 3x minus 10, x approaches 2. X approaches 2. So we did those, we worked with these limits for the first exam. Let me zoom out. Move this beautiful pink stuff over here. Good. Oh. So let's see. What did you say? Oh, let's talk about it. So let's see if there's even a problem. Remember, step 1, plug in. Maybe there's no problem. So 2 squared is 4 minus 4. That's 0. And then 2 cubed is 8. 8 minus 10 is minus 2. Plus 6. Oh, it's not even 0. I think there's a typo in my notes. Do you think it's 8? Maybe that? I wonder what we're supposed to be. Or it's a square. Oh, I can check the answer. That's so annoying. So it is, let me see. I have a factored form. So it is x squared minus 2x plus 5x minus 10. So it is, no, it says it's 3. Oh, but it's squared. That's why. Okay, makes sense. Just a typo with this exponent. X squared. 4 minus 10 minus 6 plus 6. Okay, works. Fixed it. So now I know it's 0 over 0. And then remember we factored out stuff. So instead of using L'Hopital rule, actually let's use L'Hopital rule. Now you can use L'Hopital rule. Derivative of x squared minus 2x is 2x minus 2. Derivative of the denominator 2x plus 3. If you think the answer is 2 over 2, you're wrong, because it's not at infinity. At infinity, you can perform this kind of trick. At infinity, yes, you know that's the ratio of the leading coefficients, but not at 2. So in the long run, polynomials going and following the leader, but not a 2, so be careful with other cases. Okay, if I plug in, is there still a problem? No way, because denominator is now positive, right? So it cannot be 0. So I plug in and I get the answer, and the answer is 2 by 7. How did you do it before? Before we used algebra. Or algebra. Maybe it still counts as calculus. It was a fraction, factor out x, let me zoom in. It's going to be x minus 2, and then you have x minus 2, x plus 5. That's what we did for the first exam, and that's why everyone did not like it. People who know L'Hopital rule, they know it's so much faster. Cancel out, you end up to be with x over x plus 5, and at 2, it goes to 2 over 7. See? So which one do you like more? L'Hopital rule is amazing. It's fast, it's convenient.
I think it's easier with L'Hopital rule.
It's easier also because lots of algebra and fractions make mistakes. Derivatives, if you know them, you're good. You're good at that. Just don't mess up with derivatives.
I just want to avoid algebra as much as possible.
Yes. Why does it work? Because it's in the book, yes, but also there is a whole idea behind why L'Hopital's rule works. When you zoom in, let me just explain it to you first and then read the blah blah part. Check it out. Look at this. Look at this. Here's your function, some kind of function. It's still a linear approximation, as you can see from the formula below. Slope times x minus a plus f of a. When you zoom in, functions get closer and closer to each other. So here's your animation. They actually do flatten the function out. You can see it this way. You take it and they flatten it out, but actually they just get closer and closer. So linear approximation says why not to use line at the point instead of the function if we can. Well, that means at the ratio that you can do that too. Why not to use Why not to use derivatives of functions when you have a ratio versus the original functions? That means I will take this line and divide it by another line, which is easier than do otherwise. Let me show you two graphs. I think whatever I said did not very clear it up. Sine has a slope, red color. Green color is a line, has a slope. Instead of working with sine over x, why not to work with their slopes? Since they all more or less the same at 0 anyways, so why not to work with derivative instead? If you approximate the function with a line, then why not to keep using it in the future calculations? Yes, the answer is not exact. That's the problem. So then why we say equal sign? Why there's an equal sign then here? Why it is exactly 2/7 if we know that linear approximation does not give you the exact answer? Do you know? When you zoom in at the x equals 0, functions look like lines, so we can use linear approximation. That's my way of explaining it. Because we're working with a limit. Limit doesn't have to be exact. Limit is a limiting position. We're never gonna reach 2/7, but we're gonna get as close as we want to 2/7 by 0.00001 error. Then it's an equal sign for the limit. And here's again explanation. I like these graphs. If we have ratio of these two green and blue parabolas, at the point 2, I want to find their ratios. Well, at the point 2, if I'm zooming in a lot, those are just two lines. Here's a line and blue line. So instead of working with quadratic functions in this case, why not to work with the ratio of those two slopes? The first slope is a number, say 5, and the other slope is a number, say 7, 5/7. That's how good it is. So L'Hopital rule makes sense. It uses linear approximation and also deeper ideas behind it. Basically, if you want to, I will actually write down this. If you want to understand the big idea behind it is linear approximation is used in many ways. It was a boring chapter, but so I would call blue one g of x. G of x can be approximated with derivative times x minus a. And then green function f of x can be approximated with derivative x minus a. We're zooming in at 2. Zoom at x equals 2. Thus, it will be x minus 2 here, x minus 2 here. And we find the ratio of these two. So it's going to be work with ratios. Ratio, what kind of ratio? Instead of f of x over g of x, why not to approximate it with f prime over g prime? And then x minus a shows up and x minus a, and they cancel out. So that's kind of the idea of L'Hopital rule. Why not to work with derivatives instead, since we can use line to approximate stuff? And it's a pretty popular idea. Linear approximation is very powerful tool. Not too bad? Yes? Oh, actually, I just realized also not random functions. I'm like, why did I choose those two parabolas? That's why, because these are the parabolas. I just realized. These are the parabolas I chose. Duh. It's f of x. It was in blue, I think. Let me check. F of x is green. That's what it was. It's for example number 4. It's a graph of example number 4. F of x and g of x. So this is still example 4. I see. So we're finding the ratio. This is not just a limit floating in the universe. It's a ratio of two polynomials at a specific point. And we're using lines at that point instead. Does that make sense? Kind of a cool idea. I don't know if you were impressed or not.
Can you say again why we can cancel out the x minus a?
Oh, because a is the same for both. So a is 2. Yeah, thank you for asking. A is 2. The moment we choose where to zoom in, that's what we plug to both. So x minus a and x minus a are the same when x approaches 2, or x approaches a. Are there any more animations? No, that's good. So that's very good. And the answer was 2 7ths. More examples, more interesting cases. Of course, now we're going to be plugging lots of stuff we learned before, which is exponentials, sines, cosines, blah, blah, blah. You'll be so fast at this, you will feel satisfied. You will feel like, wow, I'm good at this. So this beginning of this chapter is very empowering, and in the end crashes you as always. It's like literally every time, homework at the end always reminds you that that's horrible. But it's just the learning experience. Don't be demotivated. In fact, I am taking belly dancing classes, and I just took the Saturday class, was taught by a teacher who has degree in engineering. She received degree in engineering, worked in engineering, and then completely switched to become a belly dancer teacher, writer, performer. It was fascinating to get a class from a STEM person in dancing. She was able to describe the muscles and how they work. I was always curious why the hip goes to the left, and then we do up versus to the left and down. And she explained the gravity and how the muscles have gravity weight on the leg, and that's why you don't want to go lower for stability purposes of the middle of the mass of your body. It was amazing. She says people in the class who are STEM people will like it. It's like, yeah, I like it a lot. So she said that if it's something hard in your way, and she says STEM people know that every time there's something hard, we don't call it bad or horrible or I am bad at this. We call it fascinating. It's fascinating, and I'm not good at it yet, but I will do it later. So she says, same with dancing. Some kind of move you cannot do it. Don't say it, I'm horrible at this, I should quit. No, it's fascinating. I will do it later. I will learn later. So I really like it. From now on, I'll be calling everything fascinating. Everything you think is hard. So this limit, look at this. Is it fascinating or not? And that's how you should see this mentality of something is horrible, push you in the face, and you cannot do your homework. It's fascinating, and you just need more time to figure it out. Let's check if we can apply L'Hopital's rule. At 0, we have 0 over 0. Nice. Let's do L'Hopital rule and see if it makes it better or not. In this chapter, usually it does. X goes to 0. X to the 4 is 4x cubed. Sine becomes cosine. minus 1. I don't know. That does not look better to me. Let's check. X, yeah?
Why would it be x cos x minus 1?
Oh, derivative of sine is cosine. Derivative of x is 1.
Oh,
Yeah, just do it piece by piece. Too fast. Let me know if it's too fast. So, did not really help because I can check one more time. At 0, we have 0 divided by cosine of 0 is 1. 1 minus 1 is 0. So let's do it again then. That's the thing. You can keep going until you are done with keep going. 12x squared. Still looks horrible. But now we have minus sine x and minus 1 becomes 0. X approaches 0. Is it better? So let's see what's happening here. 0 at the top, 0 at the bottom. Super annoying. Let's do it one more time. Do you think one more time will finally be the last one? How do you know?
Because minus sin x is.
Minus sin x becomes minus cosine, and cosine at 0 is not 0 anymore. Division by 0 disappeared. We know the answer. Also, you could keep going. You will have 24. If you differentiate, oh, you cannot differentiate one more time. I just realized that. You cannot differentiate one more time because now it's not 0 over 0 anymore. So it is, let me write down, 0 over minus 1. So no L'Hopital rule, please. And also, if you want, you can keep having my little circles. But again, I will never require this. Yeah. What's the answer? 0 at the top and denominator. Yeah, I just wanted to make more steps. 0 over minus 1, which is 0. Yeah, thank you. I was like, should I say 0 or should I just make more steps? I like making steps for good notes. Does it make sense that we had to go through so much hassle? Yeah? Next. These actually go fast, so check this out. Oh, is it the same one? No, it's not the same one. Let's do... They all look the same to me, to be honest. But okay, there was a reason why I chose them. I just don't remember anymore. 4x cubed. Oh, it's the same equation. I see. It's not different. I was like, they look all the same to me. They are the same. That's interesting. They are actually the same. Huh. That's pretty cool. So then, we're going to do more examples anyways later. That was a good example. I can show you briefly the idea. It's perfect actually for 10 minutes to make a separate video about speeds of functions. What is happening with e to the x and log, for example, and so on. So let's do that. Just a second.